Hello everyone, my name is Kanav Butts and I am a PhD student at the University of Waterloo, and I'm here to present our work on event detection in coarsely annotated sport videos via parallel multi-receptive field 1D convolutions. I'll talk about the motivation behind our work. So the current work in sports event detection use frame level annotations, and frame level annotations are difficult to obtain because annotating each and every frame is pretty cumbersome. So it is easier to obtain coarse second or minute wise annotations. But the thing in coarsely annotated videos is that there will always be a certain uncertainty regarding the exact event location, and hence in this work we propose a multi-temporal receptive field architecture to account for uncertainty in event location in coarsely annotated videos. I'll talk about the network architecture on the slide. So the input of the network consists of input frames from an untrimmed video. If there are t number of input frames, then these frames are input into a 2D CNN and then we'll obtain t n-dimensional features. Now these features are input into temporal convolutional towers. Each and every row, these rows represent different temporal convolutional towers. So the important thing is that each tower has a separate receptive field as compared to the other tower. That is, each tower processes temporal information on different scales. Finally, the observations obtained from these towers are summed up and then are softmaxed to obtain the event class probabilities. The temporal convolutional towers are composed of T-con blocks, where each T-con block is composed of a 1D convolution followed by a Bash norm and then ReLU. Now I'll talk about the datasets used in this work. So we have to use two datasets, the NHL dataset and the SoccerNet dataset. The NHL dataset is composed of 10 NHL games with events face-off, shot, advance, and play annotated. We have used 9 games for training and 1 game for evaluation. The events face-off, shot are pretty obvious, whereas in the event advance, the player moves the puck without any intended recipient, for example, dump in, dump out, or clearing attempt, whereas in the play event, the player moves the puck with an intended recipient. The dataset is heavily imbalanced, with the play consisting of 80% of the events. The datasets are annotated second-wise, that is, the annotations are coarse. This is because the hockey events are quite fast and they happen in fraction of seconds, and hence we do not have the exact frames where the event is happening. Also, the event has quite a high frequency. On the other hand, the SoccerNet dataset consists of 500 soccer games with events goal, substitution, and card annotated. The events are anchored to second-wise timestamps, and this dataset has a low event frequency. Since the events are anchored to second-wise timestamps, we do not have any frame-level annotation. Hence, these two datasets represent coarsely annotated datasets. For event detection in hockey, the input consists of 30 frames for a period of 3 seconds at 10 fps. The events are input such that each tower receives frames corresponding to two events and the context around each event as an input. This is illustrated over here. This is the event and this is the context around it. Also, each tower processes two contiguous events in a single pass so that the transition between two events can also be learned. Finally, weighted cross entropy loss is used. Background event is sampled with a probability of 0.2. This is because if we do not do this, then only the background will be sampled because there is a lot of background and the learning will become difficult. Finally, we know that events such as face-off, shot, and advance do not happen or are less likely to happen simultaneously. So if the network predicts n events in a row where n is greater than 1, prediction with highest confidence is considered. For the results on the hockey dataset, a predicted event for a 1 second interval is considered correct if it is within 1 second of any ground truth. And the precision recall and F1 score for each class is calculated according to the above definition. As you can see, the precision for face off is pretty high, 77, and we've got acceptable values or F1 score for events like face off and play. Advance is not doing too good. This is because advance is often mistaken as play, because sometimes the network is not able to understand the temporal context in a good way, which is illustrated in this figure. We perform an ablation study to study the effect of multi-receptive field tower setting on accuracy and loss. T1 and T2 and T3 represent the three convolutional tower settings, such that repeating a tower 3 times and single tower settings are compared with the multi-tower setting T1 plus T2 plus T3. The loss values are lowest and accuracy values are highest for the multi-receptive field setting, which demonstrates the effectiveness of the method. For the task of event spotting in soccer, the objective is to predict anchors of soccer events in soccer game videos. The input to the network which we give are the 15-second windows consisting of the 30, 512 dimensional resonant features. The features are extracted at the rate of 2 features per second. The output is the soccer event probability. The inference is done using a sliding window and a weighted cross entropy loss is used. So this is what the output of the network looks like. So after using the network as a sliding window, we obtain the probabilities for the events in the game time. For the SoccerNet dataset, a predicted spot is positive if it is within a tolerance of del of the ground truth event. The metric is the average MAP between del is equal to 5 to del 60 seconds. So as you can see, our network achieves competitive performance as compared to the state of the art on the SoccerNet dataset. We achieve an MAP of 60.1, whereas the state of the art is 62.5. In conclusion, we introduced a multi-receptive field architecture for detecting events in two coarsely annotated datasets of different event frequencies. The results on the SoccerNet dataset are better than hockey. This is because there are more event ambiguities in hockey. For example, events such as dump in, dump out, and pass look very similar. And also the events in hockey are fast paced as compared to soccer. Our future work will be concentrated on using player level features, hockey puck position, and also using game level audio. Thank you.